Hello, this is going to be Chill Maths on Twitch, where we do maths but in quite a chill, relaxed way. I don't know why I introduced the video like that. I suppose it's of value to people watching the YouTube stream to have a real bam, let's go. People joining on Twitch, hello. Good to see you again if I've seen you before. But if it's the first time I've seen you, then hi. I'm James. I am a maths person who's always trying to learn more maths. The plan for this bit of my Sunday afternoon is to try and learn some maths. I've got a paper on the screen. That I would like to have read, and I haven't read it. So hopefully, at the very least, I'll be able to say I've read it. Hello, Murray and Mouse and Ash and Herb in chat. Good to see you. Hope you're doing okay. It's been a bit of a busy week in terms of streaming because I did the in terms of work streams. I did this regular stream for my job on Thursdays, but I was also live Saturday for what is, I think, the biggest stream of my year. We do this sort of open day live stream where we do an international kind of themed open day online, and that one gets the most viewers out of anything we do. So it was quite stressful doing a sort of live stream. And I'll tell you what, the open day live stream, very well behaved. It was a good 40 minutes before anybody said anything at all in chat. I encouraged it a tiny bit, but maybe not enough. Hi Charlie as well. There you are, Charlie 34711. So it's, yeah, getting people involved. And I hadn't appreciated how much I need. Oh, thanks, Mary. I hadn't appreciated how much I need that kind of feedback for what I'm doing. I'd done an in-person open day the week before, where an in-person open day you're always hearing about. You can see people's faces and stuff. Yeah, I'm not sure. I think my impression is that lots of people watching that live stream, it was maybe the first time they'd seen some Oxford content, which there's new people every year, so it's maybe their first time they'd seen some Oxford content. So explaining colleges and admissions processes and things like that. I've got to start somewhere, get them in early, and then we can keep doing more stuff. Charlie was in the in-person one. Hey! Yeah, and then lunchtime was... Well, we had staggered lunchtimes. I don't know, like at school, sometimes they have staggered lunch breaks. Our in-person open day had a lunch break. I wondered whether I should put a break in the middle of the morning. There's quite a lot of... We did about 5 or 6 talks, short talks, but 5 or 6 things back to back before we let anybody stand up. So it should probably slow it all down a bit. Hello, Thrice Shy as well. Yeah, break. Although, this is my sounding board now for work stuff. Hi, Neutrino. Hey, good to see you again. I'm sorry to hear you were sick. I'm just doing a sort of sounding board on the people watching this stream to try and find out about my work. Anyway, never mind. When we did an in-person open day, we did lunch in the middle of the day, roughly speaking. We did tea and coffee right at the start of the day, so that as people were turning up, if they turned up a little bit before the start of the first talk, because that's a natural thing to do, there was some tea and coffee. I think maybe tea and coffee is just not that popular with young people these days getting ready for university. Maybe it never was, but my impression was that lots of people were a bit early because that's the natural thing to be done, and then weren't that interested in tea and coffee. Charlie's given me amazing feedback to say that they were unaware of the tea and coffee. That might be it. Mary likes tea and coffee. Most people don't like tea. We had Oops. Oh, Charlie was down by the big triangles. Yeah, wrong end of the building for tea and coffee. Okay, this is helpful feedback for my job, which this is not my job, but it's helpful feedback. Next year, try and make sure people are aware of the tea and coffee, and maybe do more tea and coffee mid-morning or something different mid-morning. Break it up, get people standing up, make it more complicated. I hope that people coming on the in-person open day that we do don't noticed that it's quite a complicated event, but it is really complicated. At one point, I made an announcement to an enormous room of people, and it was not correct. I basically told 300 people that it was time to leave and go home, and it was true for maybe 100 of them, but for about 200 of them, it was not time to go home. There were more talks, and that's the sort of mistake that you make if you have a complicated timetable. Yeah, floor signs and stickers, and yeah, more signs towards tea and coffee, and the etiquette of help yourself tea and coffee. Yeah. The intention for this one, as someone supplying tea and coffee in a help yourself situation, was that there was a big urn of coffee that people were helping themselves to, and it makes no difference to me whether one person drinks all of the coffee or 200 people drink all of the coffee between them. And Charlie went to 5 different buildings. Yeah, I wonder about signage when people get there. This is now great R&D for my job. This is good feedback, Charlie. And more signs on there, like round the bit with the fountain. There's this fountain of a merman. He's got a fish tail. He's got a fish. Around there's the philosophy department. There's a little chapel. There's a building to do with health. There's lots of other stuff around. He put the etiquette next to the station, like take lots or whatever the policy is. Grabbers for crisps. Yeah, that's a good feedback. I feel that too sometimes. Yeah. Good. Right. Okay. Open day feedback. Charlie, feel free to just keep talking about the open day. I'm going to try and pivot towards talking about thermohaline convection, but not because. Yeah. Not because I don't need to hear food feedback, but I figure I can kind of multitask here. Okay, here's the scenario. This paper is from 1961. It's about something that seems vaguely important. People keep talking to me about it. I haven't read the paper. I probably should read the paper. This, I thought, would be a good afternoon to just try and do that. Not sure if we're doing a step stream today. I think I might just do this for a bit and then call it a day. Step stream was getting a little bit... I don't know. We'll come back. We're not done with step stream. I think I need to get better at step. Yeah, so notation over here. I've seen that as well. So I think curly T and curly S are fixed temperatures and salinity. I'm reading outside the wall. It's fixed numbers. Where mostly I've seen equations like this before for Newton's law of cooling over here. If you've got something hot and it's surrounded by colder material, then it will lose temperature, lose heat at a rate that depends on the difference there. Depends on the difference. Yeah, I believe that might be a curly T. The fact that they've gone for an S here and T up here, I think. Anyway, I don't think this is going to be very important. I think this is Newton's law of cooling and, for want of a better phrase, Newton's law of salting. Anyway, we're getting ahead of ourselves. The picture that people draw for me when they're trying to explain this paper to me, which happens more often than you might think. People sometimes try to explain this paper to me, and they draw this picture where they say, you see, in the ocean, there's this bit near the equator, which is hot, and let me think, salty as well. We're going to read it in a second. It's got some properties. It's maybe hot and maybe salty. And there's this bit by like the North Pole of ocean that is cold. And I've drawn these as 2 separate buckets, but of course that's nonsense. These 2 buckets talk to each other as if they're joined by pipes like this. So pipe, people will usually draw like a sort of surface pipe. I regret my pipe drawing, it's not very good. People usually draw kind of like this high up pipe going that way and a low down pipe going that way, and it's supposed to represent the flow in the ocean that takes water from the equator up to the North Pole. It sinks and then comes back down again. And there's sort of this conveyor belt or this motion of the ocean going round and round and round. Yeah, people on chat still jumping on the notation that's going to come up in a second. Okay, here's the oceanography thing that this model maybe helps you understand. The top bit, the top arrow there, is an important source of warm water into the kind of northeastern bit of the Atlantic. That means that the UK is not too cold, whereas equivalent latitude bits of Canada really cold. There's this kind of warm water effect going on. The water around here, I guess, is warmer than it could be as a result of this kind of flow. And there's a question about what would happen if the flow reversed and started going the other way. Presumably that would be quite bad news for climate in Europe. So understanding why it's going that way and what might make it go the other way is something that the reason people talk about it to me. Yeah, like I'm doing this with my finger, convection, and there is convection in the title to sort of convey this idea that things going round and round and round. And there's kind of temperature driving that, but also salinity, the saltiness of the water. So when you see the word salinity in here, that's or salts transfer or something, that's all referring to the effect of salt, which you don't learn about at school because the air is not salty. You can explain convection and talk about convection currents in the air just by talking about temperature. With water, salinity is maybe also important. So both, I guess. Yeah, so reading between the lines, I think this reversal is considered bad. We should try and understand the direction of Q. The thing I've never understood, which I would like to understand, my kind of stretch goal for reading this paper, is how the differential equations have got anything to do with the direction of Q. Because if you see in that diagram, there's a Q arrow going left to right, and there's a Q arrow going right to left. They're going both directions, clockwise. If Q reverses, then I kind of expect that to have like devastating consequences for the UK and European climate and whatever. Fine. But mathematically, in terms of what the flow is between those two boxes, I don't understand why it matters. Oh yeah. Waffle Off has googled thermohaline. Let's have a look at it. That's a good idea. Let's try and get some thermohaline currents up to get this kind of map. Yeah, people draw these weird looking maps. Let's have a look at some of them. Is my Google going to tell me anything weird? Nope, let's put Google on screen. Yeah, so I'm not quite saying the setting where people tell me about this, but the setting's not really important. But yeah, roughly once a year, people try and explain thermohaline circulation to me. And they always show me maps like this, going round and round as surface currents, which are warm, might move water around, like the Gulf Stream, I think that was called. No, is that an air thing, the Gulf Stream? Forget I said Gulf Stream. And then deep water going back. And kind of like red and blue, which makes me think of like arteries or veins moving around. Yeah, the picture's trying to show you, I think, that the cold water is underneath. It's going down. I've been showing this Britannia picture as well. Let me just have a check and see if Britannia is going to be weird. Oh, yep. It is going to be weird. There we go. Larger version. This kind of picture. This picture is just showing us effects of temperature, or it's conveying this idea that there's a role that temperature plays in these ocean currents. There's no kind of labelling here on what the effect of saltiness is. So, yeah, and then geography. Tricky questions about geography. Good question, Waffle Off. Okay. It is interesting that it goes around the Caribbean like that. I wonder if that's a question about the shape of the ocean floor or something. Or the shape of... Or is it a question about... Yeah, I don't know what's going on there. but nobody's ever tried to explain that to me. So I think that's beyond a stretch goal. For why is it doing a loop-de-loop over here? Or at least why is the picture got a loop-de-loop? Is that inspired by reality somehow? Okay. A thermohaline circulation avoids the Bermuda Triangle. Oh yeah, it kind of avoids going off the edge, right? Except for this bit going around the South Pole. Okay. So many talks where I kind of don't have the courage to ask at the end. The Q arrows are both the same. And sometimes people also add in a picture of some evaporation happening here, for water evaporating from the equator and also precipitating in the North Pole. And then sometimes people add on the extra E here to kind of close the loop, to say also there's some water that goes up into the sky. I guess kind of maybe the same water or maybe different water falls from the sky as snow and rain at the North Pole. Oh, do you think there's a feedback loop that the ocean currents could gouge out some of the sea floor? I have no idea. It doesn't sound impossible, right? I know how rivers work. Good. Okay. Right. I think I'm just going to have to start reading this paper if I want to find out what's going on. I think it's going to be a simple mathematical model, which then has some maybe complicated mathematical analysis and some stable regimes, which maybe correspond to good news, bad news. We will find out. Okay, abstract. Free convection between two interconnected reservoirs, that's the two buckets, due to density differences. Okay, so like the mass difference, expansion of water due to temperature changes or salinity or whatever. Okay, maintained by heat and salt transfer to the reservoirs is shown to occur sometimes in two different stable regimes and may possibly be analogous to certain features of oceanic circulation. Today I learned that I'm spelling oceanic wrong. Okay. So let's get into it then. I'm going to try and skim read this text at the top because I think I've done a summary of why I want to read this paper. Okay, many important oceanic regions. Oh wait, no, it's oceanic with a C. Maybe that was a typo or a transcription. Maybe those are two words. Somebody Google this. Am I going mad? Can you spell oceanic two different ways? It's an American spelling. Okay, right, good. It's oceanic with a C over here though. Oh, I'm so confused. This is a Harvard paper. Oceanic might not be a word. Oh, well, look, okay. I'm not here to rag on somebody's spelling. You've seen my spelling. Oh gosh, on Thursday we had a bit of a spelling mistake. It was pretty bad. If you were there, you were there. I'm not going to explain my spelling mistakes on this one, I think. It was not great. Okay, for example, water in and above the thermocline. Do I know what the thermocline is? I think I remember what the thermocline is. I think it's the way that the top bit of the ocean is warm because it's heated by the sun. And then at some point below that, it's really cold. I think there's a kind of cliff edge in that, which people call the thermocline. Yeah, there's a sort of transition layer. Good. Okay, I've got a Google search on the other screen. So you can't see me Googling things. Yeah, and there's a complicated atmosphere thing that I remember doing at A-level or something for how different temperatures as you go up. And you do not get a mark for saying that it gets hotter because you get closer to the sun. We're neglecting the effect consideration of the salt fountain effect. Hello, thank you for the follow, Funabi. Was it an A-level subject? Maybe it was GCSE or science or something. I just remember people telling me that the sky is warm near the Earth and then weirdly cold and then weirdly warm again, maybe. And it's got like several more surprises for you as you go up. If you'd like to read a nice book about the atmosphere, I'd recommend the one by Dr. Simon Clark, another Twitch streamer. There you go. Yeah, what up, Funabi? You can read Firmament for more. There you go. This is a quick plug. Not getting commission on that. Okay, let's carry on reading. I've read about half a paragraph. of 7 pages, including maths, which is slow to read. Okay, excessive evaporation at those latitudes. It's able to increase the salinity because things are more salty if you remove the water, because the salt doesn't evaporate. The salt stays there, thank you, and the water evaporates. Okay, so then in general, the density contrast with deep water is only 1/2 of what it would be on the basis of temperature alone. Okay, so right, so there's going to be some effects on density here. That when you heat up water, it gets less dense. I think when you put salt in, it gets more dense. And I think this paragraph is saying that those effects kind of cancel out. Let's scroll down a little bit. Here we go. Salinity kind of predominant influence. Salinity is important. Comparison. Heat, more rapid effect. Long run, giving sufficient time. Evaporation can reverse the thermal influence. We don't know. To full complexity in nature. Okay. Explore the implications of simple idealized systems. That's all we propose to do here. Oh, this is nice. This is a nice first paragraph. The ocean is big and complicated. It's got temperature and salt in it. We're going to do a simple system to have some idea of what might be going on in one element of it. Okay, here's our very simple setup to start off with. We've got a stirrer, which is going to make sure that all of this stuff is at the same salinity and temperature as each other. And we've got some porous walls. I wonder what the porous walls let through. Maybe temperature and salinity somehow, I guess. Oh, there's something called osmosis, isn't there, for water moving between porous things to balance out concentrations of other stuff. Oh gosh, this has become a science revision session. Ugh. Yes, Charlie's remembering GCSE geography in chat as well. Good. Okay. So it's being stirred, so I don't need to worry about bits that are far away from the walls or close to the walls. That's what I'm being told. They're made of a porous... I'm going to scroll up, but let's imagine that picture with curly S and curly T. Someone in chat earlier said S is already curly. You don't need to... Oh no, whose idea was this? Okay, whoops. Try not to switch to a different document. Okay, the substance is permitting transfer of both heat and salt. And here is the kind of, this thing I said was Newton's law of cooling, which says that if the surrounding temperature is hot, hotter than the bit in the middle, if curly T is larger than T, then this will be positive. I think C is a positive constant, and that'll make the temperature in the middle bit increase over time. So it'll warm up. And of course, if you switch the sign around so the bit around the outside is colder, then it'll cool down. And that rate of change is proportional to the difference between this temperature and the ambient temperature. That's Newton's big idea, I guess, is that this thing's just proportional. Which tends to give you, if you've seen differential equations like this before, you'll know that this looks like a kind of exponential, right? If I show you this one, so if I ignore curly T for a moment and just give you this, so this differential equation you can solve. It says that when you do the time derivative of y, you get minus c times y. So that one you can solve. Maybe this one you need an extra bit of help with. So if I have a constant in here, which I guess for consistency I should call big Y, some sort of constant, and that's like an ambient temperature or something. You can also solve that differential equation. You can do it. I believe in you. And there's a particular integral you need to that gives you a constant that you end up at. The constant is big Y. Yeah, I guess you could do a separation of variables. I would accept, to be honest, just writing down the general function that does that. I don't know. I guess it is, yeah, separation of variables and then integrate and then rearrange. And over here, oh yes, this is still separation of variables, isn't it? You just have a slightly different logarithm. So what does C depend on? So C is something to do with the rate of change. And I think it probably depends on the properties of the porous wall down here. How easy is it for temperature to change, given that there's a different temperature on the other side of the wall? So some sort of thermal conductivity, maybe. And it maybe depends on, I don't know, how many holes there are or something, or like materials and geometry is kind of the cheeky answer. Yeah, like conduction, or it's always kind of insulation, but here we're not really thinking about it being insulated, we're thinking about being porous. So yeah, that'll happen. Yeah, so now we're going to make them non-dimensional. And this is something that mathematicians do with equations to it's a good idea generally if you're going to give a differential equation to a computer. I think this is an opinion. It's a good idea to give it just numbers to work with, rather than telling it, the temperature out here in the ambient is 300 Kelvin, and this C is once per hour. It's got units of like per time. So it's like once per hour. If you can divide things and make these just numbers, then in some sense your computer's only working with numbers and not things that actually have dimensions on them. So just a number in the sense that well, C is actually technically a frequency. It's got units of hertz, and so does D. And these are maybe different frequencies, but if possible, you want to try and work with equations that are simpler and don't involve, if possible, don't involve quantities that have dimensions on them. Sometimes this lets you convert lots of different problems with different constants in down to the same equations underneath. For example, if I'm solving dy by dt is, I'm going to write out the same thing again. Dy by dt is ky, where k is 3 hertz or something. And it's also kind of mad to think of that being in hertz, but never mind. With y of 0 is 1, and I didn't tell you this, but y is actually the height of a building or something, so it's 1 meter at time t0. Time is in seconds, I guess. Then something sensible you can do, rather than working with all these hertz and meters and things, is to say, okay, well, I'll do y divided by its initial value. I'll do time divided by a relevant time scale here, so divide by a third, and to just divide things down to get some non-dimensional constants. Yeah, it means there's no units on it, in a way. Yeah, I like that. I suppose your computer doesn't work in real time, is one thing as well. It doesn't need to sit there and actually have 1 second being 1 second. So it does all its calculations, and then you can do some interpretation of what the answer means. Yeah, does non-dimensional sound really good? Like it might be 0-dimensional, like 3-dimensional, 2-dimensional, 0-dimensional. Ooh. Yeah, no, sorry. Okay, they're just telling me that they can simplify the equations to get some sort of nice value. The thing I need to remember is that x and y don't mean position. X is going to be salty, and y is going to be hot, which I suppose those are adjectives, but whatever. So when I see y, I should think hot, and when I see x, I should think salty. There are the different equations. And you see how these are a little bit simpler. There's no constant out here anymore. The idea being that we solve these differential equations with some number delta in here, and then reinterpret them for maybe a particular problem. We know that C is, well, it'll take 10 years for this thing to equal out. Yeah, so you rewrite it in terms of things like delta in here is literally a kind of proportion. It's d divided by c. And this is kind of good because if you're studying 2 different oceans or something, or if you've got lots of different applications of this idea, then being able to just take your differential equations that you solved and reinterpret those solutions for different cases lets you apply it to lots of different things. It's a pretty powerful tool. Hello, Super Snowman. We're trying to read and understand a paper about oceanography. It's called thermohaline circular convection. The idea is that in the ocean, there are kind of different bits of the ocean that have different temperature and different salinity, and they're connected by these kind of convection currents that travel quite slowly over great distances, but exchange water between places like the equator where it's hot and places like the North Pole where it's cold, and you get this kind of conveyor belt of water. I've never really understood the maths that's in this paper, so I've decided to bite the bullet and actually try and read it. Okay. We're most interested in situations where salinity transfer coefficient is less than the temperature transfer coefficient. Okay. Right, okay, we're going to try and speed up a little bit. There's the solution. If you were playing along at home and you found some exponentials, then here are some exponentials. And these things quickly get towards the temperature approaches asymptotic value more quickly than the salinity. Fine, okay, we sort of sounds equivalent to this stuff we set up here. Okay, here's an equation of state, which usually means something about the density. I can see the density coming up here. To tell me what the relationship is between the density of the water. It tends to expand when it gets hotter, which is lower density, minus sign, and the density tends to increase when you put loads of salt in the water, because now it's heavy with all that salt that you put in. So plus sign here, beta. And we've got some non-dimensional quantities for x and y, some numbers come in. Okay. So we can talk now about the rate of change of, the time rate of change of density. Yeah, okay, if you make it hot and salty, you've non-dimensionalized. Lovely. So you can now talk about things being just the number 1 or just the number 0 after you've non-dimensionalized. So that's nice. Yeah, and this one is a little bit, what if it's all just linear and nice? It closes out the problem, so mathematically it's kind of good to have something like this. In reality, density depends on temperature and salinity in a very complicated way. If you like, there are more correction terms that you could put on after that one to explain how the density actually changes. If both temperature and salinity change, is it expected to go like the sum of those effects or like the product of those effects? Who knows? Okay. Sure, so then we've got some effective density changing, and I wasn't really paying attention to this bit, but I was skim reading it. Okay, so as this thing's getting to equilibrium, then its density might change. It doesn't seem very oceanographic so far. Where are these? Where am I supposed to imagine these big porous walls and things? But okay, I know there's a 2-bucket model coming up in a moment. 2 reservoirs is the technical thing I suppose I'm supposed to say. Sure, okay, so at the top there a salinity temperature thing that I'm not sure I mind too much about, to show how that will change over time. Lovely, okay. Grand, at different times, different temperatures, different salinities, but this is just the things approaching their equilibrium values up here. So it's just approaching that corner along some curve, which I think I'm understanding is fast and slow dynamics. Anyway, so that got values of alpha and beta in it then. Oh, look, not important right now. Yeah, big R is 2 for the kind of ratio between beta and alpha being the thing that matters. Okay. Yeah, good, okay. I'm pretty sure there's 2 buckets coming up. Different rates. Yep. Lovely. To consider a simple steady state process in which the water. Oh right, we're going to now add water in. Water that's, I think, cold and not salty. Fresh water that's cold. Flows into the vessel at rate Q. And the mixture is withdrawn at the same rate. Oh right, okay, this is the thing people are always talking about. For the conveyor belt thing, right? You've got one sort of water coming in on the conveyor belt and kind of a different sort of water being removed. Yeah, like ice melting would be good. Yeah, I like that. I can't remember much physics, but I think ice is not salty, and I think ice is cold. So if I need a source of cold, not salty water, sure, yep, ice melting, snow or something lovely happening in the North Pole, perhaps. Well, I don't know. Maybe we're not at the North Pole right now, but mathematically. Anyway, they're going to try and justify some different differential equations. Thanks, Charlie. Yeah. The salty thing, I have to maybe go and do a science experiment. I think you can make salty ice, Herb, by putting salt on ice. But I think the result of that is... I don't know if you can get the salt in the ice. And Wiffleoff thinks that polar ice is probably very salty. Okay, time for a really stupid Google search. And I say stupid in a kind of lovely way, because you should always try and identify which things you don't know, and then those are the things you need to try and find out. So I'm going to try and Google, is ice salty? When seawater freezes, this is NOAA, when seawater freezes, the ice contains very little salt. Maybe it sort of pushes it out. Icebergs do not have any salt, says West Texas A&M University. Okay, I think ice is not salty. If you put salt on it, then sure, I think you've made salty ice. I have to accept that, I think. But if you freeze some salty water, I think the ice that you get is not salty, even if the water was quite salty. You freeze some normal water, you freeze some salty water, you get ice. I'm showing it at the top like an iceberg or something, but the ice is kind of the same. Yeah, and how you do that, what it takes to create that ice, the freezing point or whatever, is very complicated, I'm sure. But I've seen people put salt down to try and lower the melting freezing point of ice. Good. Hello. Welcome to chat. I'm glad it was salty ice that got you into Twitch chat. Right. Yeah, I think it's at the bottom of the bowl, Charlie. Yeah. And I agree. This is something that I think it's kind of around the outside. Hello, Marco, as well. Everyone's joining chat now. We found the correct thing that people wanted. Yeah, kind of crystals. I'm not very convinced in myself, right? What happens if you freeze salty water? Is the science question of today on the Chill Maths live stream. And one hypothesis is that freezing salty water is a way to separate the salt from your water. I guess the ice will float, so it'll be ice on the top, salty stuff at the bottom. Oh, Woofloff has got a quote. And Charlie's going to do an experiment. Ha 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 ha. You can try this. Yeah, you can do this at home. We could all be doing this now instead of Twitch streaming. Brilliant stuff. I kind of love the quote. Is ice salty? Yeah, you can put salt on ice. That will make salty ice. Brilliant stuff. Okay, right. Okay, we've got a new differential equation. To get some maths in the Chill Math stream, we've got a new differential equation. Why on earth are they saying that both these things are 0? Oh, because so we're talking about steady state now. So they're imagining that. Oh, this is weird. Okay, so they're imagining that there's a stirrer going and things are trying to get towards equilibrium with the bit on the other side of the porous walls on the outside. Big reservoir of, I don't know, very salty water that's also very hot. But mischievously, somebody keeps adding in cold, not salty water, possibly from ice cubes, cold, not salty water, and removing mixture water. So it's going to maybe balance out. Hello, Marco. I'm trying to understand a paper about oceanography. It's got some maths in it. Somebody tried to explain it to me the other day, and I had some pretty basic questions. like it turns out, I don't know if ice is salty. So I'm going to try and actually read the paper. We're at the end of page 2, so it's going, I would say, great. Okay. Marco, chat is talking about whether or not when you freeze salty water, the salt gets separated from the ice. Okay, right, good. Okay. So this is the rate of change that we had before, but somebody's added in minus QT. Because, let me think about that. You had some mixed up water. Somebody replaced a bit of it. So this bit is now gone. At rate Q, fine, okay. And they put in some sort of rubbish blank water of value 0. Value 0 in a temperature sense. I don't think I mean absolute 0. I don't think I mean that. I think something's happened with our non-dimensionalization where... What does T0 mean? Back over here? No, big T is just 0. Okay, we'll just pretend that means 0 Celsius. Everything's up to a shift anyway. I'm going to pretend this paper's in Celsius. Blank water, yes. It's T0 and S0. The only two properties I care about. 0, 0, 0. I guess I'm imagining that to try and close the loop, I'm imagining in my head, and this is not really going to make sense, but I'm imagining that somebody's removing water at rate Q that had temperature T, but also adding water at rate Q that has temperature 0. So this is me trying to reconcile what the text says. The text says we're adding water and then removing mixture. So I was kind of hoping to see both of those terms. But of course one of them is 0 because that water is blank, no temperature. Right, good. Okay, this is the sort of effort that I like to try and put in to understand the link between the maths that I'm looking at and the text that I'm looking at when I can. Sometimes I can't understand it. Good, okay. So steady state means that you'll get a particular temperature that will be a bit different from curly T. And we're going to non-dimensionalize, so all these are going to turn into X and Y again. Ugh. But this will manage to keep it cold and keep it not salty, because we're constantly, it's trying to get up to equilibrium, but we're constantly removing stuff. Okay, here's the picture of inflow and outflow. I should have looked at that first. There are equilibrium values, something to do with F prime. I wasn't paying attention to what F prime was, but I'm sure it's fine. F prime is fine. Oh, yeah, okay, so it's a different sort of F, maybe? What is this? Non-dimensional forms before. Was there an F over here? Look back. No, where's F? What's F? Was it the bit I wasn't really reading? No. It's something to do with Q. No, all the F's are the same. I don't know why it's F prime. I think it must be something to do with Q. We can sort of work this out, right? One of the best things about maths is to try and just work it out. Work it out. Do. So if I take this equation equals 0 and I divide it by C curly T, I've got to try and write a curly T. That's the letter J. Oh well, I tried. If I divide it by C curly T, then we'll get 1 minus T over curly T minus Q over C T over curly T, and then this one will have a Q over D. Yeah, I'm getting ahead of myself. So I think maybe then this will be 1 minus Y minus Q over C Y. So I think F prime might be Q, non-dimensionalized by C for this competing rate, the ratio of the rates. And then this equation will make sense, I hope, if I divide by D curly S. An opinion in chat, if you've just joined us, opinion in the chat is that this paper has curly T, which is too curly and doesn't look like a T, and has curly S, which is not curly enough and doesn't look different enough from S. We're going to divide this one by D curly S. Yeah, delta was... I hope delta was D over C, because delta is a bit like the letter D, and you normally go with like the top thing. Something like that, though. A cool person. Thanks for the reminder. Because, yeah, hang on. So I'm going to divide this by D curly S, and I'll get 1 minus S over D curly S minus Q S over D curly S. One of the challenges, especially when you're taking notes in a lecture, and the challenge of reading mathematics and taking notes, is to try and imitate the notation. Yeah, nobody's good at that. I now think they've divided by C, actually, because they've got deltas, and I've got 1. So maybe they've taken this equation and divided by C to get this, or C curly S instead of D curly S. Oh, that would be good, because then you would get F prime over here as well, and that would be why these F primes are the same. Okay, I think I've made sense of how this dividing works. It's not that, it's this. Goodness me. Okay, and then bring those terms together. Good, okay. And then divide to get your steady state. So this is explaining how if you have a bit of influx of t equals 0, s equals 0 influx, then that changes the kind of steady state temperature and salinity in here by reducing them a bit according to these fractions. Okay, still don't have any closed loop flow that I was hoping for, but we're getting there. We've got flow in now, that's good. The water which entered the vessel has 0 density anomaly. We're now going to run the calculation on density. Okay. The picture shows D over C is 1 over 6. The actual point space line choice. Flow rate F prime. The shape of the curve depends only upon delta. Do you see, this is the sort of thing that you get to say once you've non-dimensionalized. Once you've non-dimensionalized, you get to say that things depend only on the ratio between two things. If you don't non-dimensionalize, you might be solving this thing for D equals 2 and C is 2, and then solve it for D is 4 and C is 4 much later, and not realise that this is the same thing. Yeah. I prefer subscripts and hats. Sometimes people do little hats like this, or tilde like that, or I think there's a suggestion in chat that we do some sort of subscript. We've also seen a lot of primes like that. We've already got F prime in chat in the paper. So there's ways to decorate your variables in order to create more letters that kind of indicate that they're related, but have subtly different interpretations. Good, okay. If you like putting hats on things, and if you know about LaTeX, then you might be interested in the LaTeX Real Hats package, which is an add-on for LaTeX that makes all of the hats that you're using into actual hats, so that instead of a little arrow sort of shape, you get a picture of a hat. That's by Matthew Scroggs, who you might have seen on QI with the Menace Matchbox thing, or you might have seen the Matchbox thing on Matt Parker's channel. You might be in the Finite group live streams. Anyway, I can't remember if Matthew Scroggs is the only person who worked on Real Hats. Sorry if I was supposed to credit Townsend as well. Who'd you credit? It's on Scroggs' GitHub. Who do I credit? Also Adam Townsend. Sorry, Adam. When this paper was written, they didn't have Scroggs and Townsend's Real Hats package, so not an option. Anyway, I'm stalling because we're getting to the halfway point and we still haven't seen any oceanography yet. Ooh, almost getting to 3 o'clock as well. Right, let's go. Okay, that's pretty sensible. If I need to understand some what do we learn from doing this? Then I'll come back and look at this. What do we learn? Remarks made in the introduction as stated. Yeah, okay. Suitable to use as a basis for exploring further consequences of the density transforming process. In particular, the fact that flow rates in free convective systems depend upon the density differences themselves. Ooh. The flow that you get depends on the density differences. So whether the flow rate is, well, I'm interested at the end in flow rate going forwards and backwards. Did they update the hats package to have the new one? That's cute. Okay. Kind of feedback of the density difference produced upon the flow rate, which produces it, now must be introduced into the system in a simple way. Introduce another stirred vessel, as shown in Figure 5. I think we're getting there. A large overflow at the top, so that the free surface of water is level. Connecting at the bottom is a capillary tube with resistance K, is such that the flow in the tube is directed from the high pressure vessel towards the low pressure velocity by a simple linear law depending on the density difference. Let's have a look at this picture then. What's a picture? Okay. So the author, Henry Stommel, just told us about several features. Here's what I picked up. There's now 2 of these. This is getting out of hand. And there's a free surface, which I think means the point. I think the point of that is that a gravity density, things will equilibrate. They're not kind of separate pressurized vessels. They've got the same. Oh, now I'm getting technical. Water will flow downhill. If it gets too big on one side because of density change, or there's water over there, it'll go downhill. So it should equal out like the density differences, I think. Maybe this is sort of the flow through this pipe given by the pressure difference, I was going to say. But the pressure here is something to do with the depth of the water. So the pressure there is just like talking about the density difference. Yeah, it does look like a chemical cell or something. It's the kind of battery shape of it, isn't it? That does that. Herb is having flashbacks to every course. I think Charlie was talking about chemistry and biology at one point as well. Yeah, we're doing everything at once. Maybe some maths in a second. Great. Okay. We're going to kind of ignore the fact that this says negative temperature, or we're going to strongly insist that this is in like Celsius or something. Maybe it's in Kelvin. It's 1960s. Who knows? Doesn't really matter. Okay, but mostly the stuff around here in the diagram is playing quite an inactive role. It's making sure that there's... no, that's not really fair. I'm excited by this flow through the capillary and through the overflow. It's kind of ocean circulation going around like this. And okay, there's some background that's trying to get this hot and salty and get this cold and not salty. I guess that's important. It's going to drive the flow, maybe. Okay. So the flow Q is positive if directed from vessel 1 to vessel 2 and negative otherwise. There is, of course, a counterflow of the same amount returning through the overflow so that the volume of each vessel remains the same. So here's something I hadn't appreciated that this is trying to say about oceanic currents. The idea is that the density of the water is different in different places. And therefore, at the bottom of the ocean, or at some given depth down in the ocean, the pressure due to the water above you, the kind of weight of water above you is very closely related to the pressure there. That pressure is different in different places, which causes a flow. from high pressure regions, where you're underneath lots of heavy water, to low pressure regions, where you're underneath some lighter water. And that flow is down at the bottom, where the density difference matters, that you're underneath all of this water. And maybe that's important for me to distinguish what the difference between a flow down at the bottom of the ocean versus a flow at the surface is. It's the flow down at the bottom of the ocean that's driven by the pressure current. The matter's then confused a bit for me by the fact that there's an equal and opposite flow to keep everything the same volume. But maybe I should be thinking about it like that, that deep down, underneath the waves, the weight of the ocean bearing down upon you, the density difference causes a flow due to the pressure differences in different places. I could kind of get behind that. Okay. So that's why this capillary is being drawn way down at the bottom here. The water here is being weighed down by the density of the water over here. And this water, which is colder, less dense, so the column of water here doesn't weigh as much. It's just being pushed by gravity through this pipe. Okay, let's read about the maths. Yeah, negative salinity is also freaking me out a little bit. I think all of these are defined up to a shift in axis. The way the ocean salinity works, I suppose, is that all of the ocean is a bit salty, some of it more so than others. So you have this kind of background salinity, background amount of saltiness, where then you could have some sort of variation around that. So when people say negative salinity, or in this model, negative S, negative curly S, they don't mean less salty than fresh water. Relative to a reference point, I think the maths is going to be fine. Was the blank water actually a bit salty? I think the answer is yes, background salinity, but I guess a bit like the non-dimensionalization, removed the kind of scale from the temperature, so that we were just looking at temperature 0 and 1. A bit like rescaling, I think we've also done somewhere, maybe before the paper was written, we've done this kind of correction to just talk about the changes from average. Baseline sounds better than average. I think the blank water would be a bit salty in practice. Yeah, and then you're talking about the salinity perturbation from that, and everything's good. The reservoirs are actually describing a fixed perturbation from the background salinity, and the time derivative is just the rate of change. Newton's law is nice. Newton's law just depends on the difference. So Newton doesn't care if you are a cannonball that's been heated to 100 degrees surrounded by 0 degree air, or whether you're a cannonball heated to 10,000 degrees surrounded by 909 minus 100 from that same difference in a furnace. Newton's law is nice under translations in temperature. I really fluffed that. Might have another go in a minute at describing that kind of property of T minus background temperature. Doesn't matter where you are on the temperature scale. Okay. Counterflow solvent returning. Solution of the symmetric form. Ooh. Okay, yep, good. This is just saying we've done a good setup of symmetric around the background thing. It's not mentioning this background salinity I keep saying, but I'm going to imagine it anyway. So we've got conservation of salinity and temperature. Why is it being conserved? I'd have guessed that it was being added from the reservoirs. Well, I suppose it's not. Yeah, I suppose that's what we're saying. Yeah, okay, it's being added by the reservoirs, and there's this. What is this doing? It's got mod signs on it, which is a bit exciting. Okay, I think this is the point where I understand some mod signs, so that's exciting. So the temperature changes, partly because it's getting a temperature change from the outside, partly because mod twice Q is something to do with the temperature change there. Bearing in mind that this water, we were adding blank water before, but now this pipe is adding temperature T2 or like minus T or something. This one is taking away temperature T water. Sorry, it's quite annoying that the picture is labelled T2 and they immediately say that T2 is minus T1 or minus T and then drop all the subscripts. It's a little bit annoying that the pictures don't quite match the text. Something else to understand along the way. So, okay. Oh, that's interesting. So whichever way the picture's going, that always acts to decrease. No. It always acts to average out the temperature. Always acts. Okay, so if I'm looking at some temperature that's above 0, above average, then this will always be negative, always bring me back, because I'm losing some hot water from this tank, but I'm gaining some cold water from the other tank. Twice Q, because there's 2 pipes and they've each got rate of flow Q. Still, mod 2Q. Yeah, okay, the way I'm thinking about it now is that mod Q is the only thing that matters. Mod Q should always be mod Q, I think. Absolute value of Q. If it's going clockwise or anti-clockwise, I don't really mind. Wait, if I just look at it from the other side, no, okay. I did clockwise, anti-clockwise, and then I thought, what if I just look at the picture from the other side? It's not quite right, because looking at it from the other side also switches vessels 1 and 2. Okay. Mod Q. I think I believe in mod Q. I'll keep believing in mod Q. Taking away some hot water and giving me cold water. Or, worse, vice versa. Ugh. It's a bit heads I win, tails you lose, right? Both of these effects have the same effect. Anyway. Oh yeah, I should just read the text. Insensitive direction of circulation. Brilliant stuff. Love to read it. How many times would my problems be solved by just reading the next sentence? You could all see that as well, couldn't you? You'd all read that. I'm going to quickly read the next 2 sentences to get ahead of you. Previous notation, define some stuff. Appropriate non-dimensional forms. Yep, great. I love non-dimensional forms of equations. Yep, what's up here? Yeah, lovely, with mod signs on the F. I've lost track of what that is. Flow in the capillaries in there. Oh yeah, okay, so changes in density drive the flow. So this is ruled about the flux, flow, Q. I'm trying to think of synonyms for what F might stand for. For the flow, Q, for the flow, F. No time derivatives, okay, good. Put that in there. Here are some equations. So, ooh, these are quite complicated, aren't they? Right, okay, so let's try and understand this. This one is describing density differences cause a flow. There's a number lambda in there, which I think is a constant. And there's a number r in there, which is a constant. Capital letters, Greek letters, curly letters, we got them all. And up here, this is the change in... I forgot which way around X and Y are. Oh, I had that guide earlier, didn't I? Is it X is salty, Y is hot? Quick look back to over here. X is salty, Y is hot. Yes! So it's interesting seeing people's notation changes, right? I guess X comes before Y in the alphabet, and S comes before T in the alphabet, so they're kind of in order. Okay. Last equation, the first two. Oh, I also have a y equation at the bottom of the left column. Zoom out a tiny bit if I can. Can I zoom out? Yeah, we're going to go tiny vision for a moment. Take the 1,000-yard look. There's an equation down here for the temperature. There's an equation up here for the saltiness. There's a density change, and these are going to be non-dimensionalized into these equations, which have some absolute value signs in. Okay. And just thinking, if the sign changes, then it's the same differential equations, right? If the sign of Q changes, then it must be the same differential equations. Okay, good. We're zooming back in. Solve the equations, which doesn't look too hard, or looking for steady states where they stop. If they reach a steady state and aren't changing over time anymore, then these equations on the right hand side will be 0. Expressions will be equal to 0. Right, and then there's going to be some simple graphical construction, which is going to be this complicated picture over here. Okay, these look sensible for the stationary state. And then here is the flow that you get, which depends on that amount of salinity and the amount of temperature difference between the two. Oh my goodness, right, okay, so here is, oh, this is rather jolly, look at this. On the axis is F, which is like the flow or flux or something, which is different for different, oh my goodness. Yeah, this is good. So over here, look at this complicated expression. This is trying to describe how at the steady state your values of temperature and salinity are a little bit out of whack because you keep adding water from the other reservoir, which is being held close to the opposite value. So you're holding your left one maybe hot and the right one cold, and the flow between those keeps the stuff in between kind of out of balance. But it's also that out of balanceness that causes the flow, because that causes a density difference, pressure difference, flux in the small pipe at the bottom. So we've got, in a way, flux F on the left. Here's the equation for how the flux depends on salinity differences and temperature differences via density differences. But on the right, those very salinity differences and temperature differences are because there is a flow that keeps replacing the water with opposite water from the other side. I don't think I'm using precise language, but I'm trying to get an impression of what this thing is. So anyway, they've drawn an incredible picture down here with, what am I looking at? Two choices of delta, 1 and 1/6. That'll change the curve on the right here, which I think is the one that's got a sharp bit at F equals 0 because of the absolute value signs. And some sort of shape like this. Whoop, and then down. And then towards 0. Which is already pretty weird. Whoop, and then down. Ah, yes, delta is 1/6. And up here, delta is 1. And in both cases, they've taken big R to be 2. Okay, so we've got these different curves, depending on R and delta. And then, you might get one steady state, or you might get, what is that, 3? So different values of lambda give you different straight lines on the left. I suppose you could divide both sides by lambda and then just talk about it being like another thing that you can change. You can change delta, you can change R, you can change lambda. How many solutions are you going to get? How many numbers make sense for the value of F? It kind of all has to be consistent, I suppose. That's often where you get equations from, things being consistent that, well, if I had such a flow, then I would get such density difference, which would then create the flow F. Did that all make sense and get me back around to that value of F? So you can think of it like that, I suppose. And there might be different numbers of values that do that. Excuse me. Right. Okay. So I think this is quite complicated. This is showing me different cases at the same time. I think I want a quick Desmos. To try and show that function on the right hand side, which depends on delta. So I'll take a value of delta as 1/6, and R. R, and what do I want to do? So I want to do something like, how do you make Desmos do stuff like this? -1/1 plus mod x. I'm going to use the letter x so that Desmos does the same thing as me. Shows me the picture, sorry. 1 plus mod x divided by delta to get this picture like this. Okay. Oh, and I can zoom out. That's the advantage of having it in Desmos, right? I can zoom out. If I do something like this, it's a bit daft. So I want a slider for delta. Don't know how to convert that into a slider. Oh well. And then on the left I've got lambda f, so I think I want a lambda as well. I'm trying to keep up with the choices. Oh dear. Okay. So different values of r. Ooh, that's fun. Different values of lambda might have different numbers of solutions that make sense. Huh. Different numbers of solutions. And the solutions are kind of intersections between these two graphs. I'd like a slider for delta as well. That's one. Hey. Okay. Ooh. Well, what's happened there? Oh, well, that's gone very bad. Maybe delta has to be positive. Okay. Weird. Okay. Feels like sometimes there's some solutions over here. I guess I can make lambda negative and get solutions on the other side. But maybe all these parameters are positive. Yeah, me too. It's the thing about abstraction, isn't it? You end up not really knowing what's going on. So F is the flow rate in a small pipe, more or less, up to some constants that don't matter. F is the flow rate. We would like to understand how large that is. Delta is a term for a comparison between how quickly the temperature equalizes versus how quickly the salinity equalizes, one way or the other. Yeah, I think 2Q. I think Q is the flow rate, and 2Q is the flow rate if you allow for both pipes. And then something's been divided by C to give me this like F, this non-dimensionalized number. So that on the axis is just numbers. But I'm still thinking of it being basically just flow rate Q. The variable R is something to do with how density, density depends on temperature and salinity. The ratio of the sizes of those effects is R, in a similar way to how delta is the ratio of the conductivities or something for temperature and salinity. R is the ratio of the density changes for temperature and salinity. And then I haven't got track of lambda. Here it is over here. So I think Q is the real flow rate, and then F being 2Q over C is a kind of convenient thing to get rid of the factor of 2 and to make the thing non-dimensional. Lambda appears to be a whole mess of things. Basically something like K. What was K? Oh dear, right, let's back up slightly. Was K something to do with... Nope, I've forgotten what K was. Where did we first see the letter K in this paper? Not the first time I saw K, ever. Where did I see K today? I see K. Spells ick. Yeah, resistance. I can't remember where it actually turned up though. It feels like a kind of resistant thing. I used a K at one point. It wasn't over here. Is it a recent addition? For this flow rate. This flow rate Q depends on. It's going to be the flow rate Q, I think. Flow rate Q. Yes, resistance in the pipe. You just saw it a bit below. Resistance in the pipe, so that, oh gosh, right, okay, density differences might not give you the flow in terms of just that density difference. You need to multiply by resistance. Okay, right. Gosh. And I guess the non-dimensionalization is saying you can compare that resistance to change against all the other sorts of resistance to change we've seen today, including one built out of, over here, rho naught alpha, for how the density would change if t changed a bit. Oh my goodness. I might leave that alone. Something to do with the relationship between density and the actual flow, which is also the role it plays over here, non-dimensionally in this equation. So maybe I prefer it just being a number lambda. That if I have an actual ocean, I could go and look up the values of some of these things. But mathematically, this combination is the thing that really matters on the left here. Okay. So then there's a famous picture. Oh no, there's a stability analysis. Oh, look at that. Ooh, it's all going on there. You've got maybe 3 fixed points, A, B, and C, in the picture. A over here, B and C. And the line showing what actually happens when you solve the differential equations, where you might approach this one, or you might end up at this one. And this one looks unstable, you never end up at that one. You may be getting close to it, and then you can do this one instead. Ooh, this is a very abstract picture on the right, showing not what's going on in real space or anything like that, but showing how the temperature and salinity change over time. It's got all these horizontal lines in here for density, which I'm trying not to think about too much. And then the arrows with the lines with arrows on are showing what might happen over time for an actual solution. Okay. You might get 3 of these. 3 different ways in which the simple convection can occur without change in time. So 3 kind of steady states. Or then if you make lambda too large. Okay, if you make lambda too large, if you allow a lot of flow, there's only one fixed point. Lots of flow, one solution. Okay. For certain choices of the parameters r and delta, there are forms for which no choice of lambda reduce 3 real roots. Okay, whatever. Good. Okay, there's some combinations of the triple where, yeah, okay. Necessary condition for 3 intersections. Some complicated maths to think about. In decimals, you sort of think going positive and negative to think about when it's going to change. Lambda must also be small enough. Okay, whatever. Look. Okay. Right. Okay. Yeah, let's look at the flow. So this bit down here is describing the flow. Method of isoclines, great. Both A and C are stable equilibrium points. I know how to do that analysis. Method of Poincare. Can we show that point A, I learned that at university, is a stable node, yeah, stable spiral, yeah, good. Okay, that picture you saw where it was spiraling or just collapsing. Saddle point, unstable. If you perturb it. Okay, very simple convective system, such as he described. 2 distinct stable regimes can occur. Some of them with F positive and some of them with F negative. Which I still sort of believe in, yeah. Okay. similar situation may exist somewhere in nature. Oh, I like this. I like this attitude. We've done some basic research on a very simple model. Maybe that's going on somewhere in the real world because it's simple. Are there quite different states of flow permissible in the ocean or some estuaries? And if such a system might jump into one of these with sufficient perturbation. Fraught with possibilities for speculation about climatic change. Such perturbation could be in a momentary state of a system. Don't want to be in the unstable one, do I? Slight change in parameters might change the state that we're in. If lambda were to become slightly greater than 1/4, the two intersections A and B would vanish. Thus, in the system depicted in figure 6. Have we had figure 6? It's figure 6. In this situation, changing lambda a bit would remove some of these states. So instead of having some fixed points over there. Okay. So I don't know how you know. I suppose you don't know which one you're in. If you've got 3 of these plausible values, there are kind of 3 things that the tank might be doing. One of them's implausible because it's unstable, but the other 2, we saw those traces. Depends on where you start. That sounds fun. Got half an hour. Okay, I think we're actually getting towards the end of this paper. There's a table with some numerical calculations on stability of equilibrium points, which is not something I'm going to look through in detail. To look at the notes, the types of fixed points in there, and there is an appendix to look at the stability. But so I was quite happy with that as well. So that's what's going on in the appendix. This doesn't do as much as I thought it did. I guess other people have done further work on this to talk about. Yeah, look, there you go. There's things approaching into a fixed point. I guess something I can do that the paper can't is to try and numerically solve the differential equations. So I think that's an option I've got to try and understand this a little bit more. I'm going to try and see if I can see some of these lines. Maybe, hang on, maybe they have solved. No, maybe I take that back. Maybe they have solved numerically in order to make this picture. Now that I think about it. Yeah, that's not a sketch, is it? A few sample integral curves. I take it all back. They've solved the differential equations. So maybe I want to do that. Yeah, okay. So what this doesn't have is a picture that I've seen before of what f is in these different cases, to talk about whether it's kind of forwards or backwards. What would you change? So you can change multiple things. In particular, as you're doing this experiment, if Q hits 0, then this is kind of interesting. I don't really know what happens in this. I think, separate from all of the clever non-dimensionalization and the analysis of the steady states, I think I want to know what's going on with this. If I could cut and paste one thing. So this is the case with the symmetric tanks. One's hot, one's cold, and the water's exchanging between them based on some flux. Oh, I suppose my box should also contain that rule about what the flux is, which is something like, let's try and find that. Down here, there's a rule about flux. No, haven't found it yet. I'll put a box around that. That's got rho in it, so I also need to put a box around some rho to talk about the density. Yeah, I think this would be a useful thing for me to do, is try and piece together these things. Yep, okay, let's try and piece this together. I will need a quick whiteboard to doodle on. Let's go to this whiteboard here. And let's switch to doodle on whiteboard. And then if we've got time, might do some live coding. Chill maths that's chill. Like water of negative temperature. A concept that we're trying to get our heads around today. Oh, if you're watching at home, don't forget to look away from the screen occasionally. Drink water. Yeah, here's the step whiteboard. Let's try not to think about that too much. Away from the screen, drink water. Neutrino's telling us to hydrate. Remember to drink water. Neutrino, do you know where I've put the pen for this whiteboard? Oh, there it is. I found it. Okay. So 3 things that I put boxes around there. Rho is rho naught 1 minus alpha t plus beta s. The change there. That's how density changes as you change temperature and salinity. I put a box around the idea that our flux be 1 over k times the density difference. So I suppose that's rho 1 is rho naught times 1 minus alpha t1 plus beta s1. Yeah, so alpha and beta are parameters, they're constants. And I'm going to say vaguely constants to do with the ocean. Rho naught for the kind of normal density of the ocean. Don't ask me how dense ocean water is. And then if you change the temperature, it changes the density a little bit because water expands when it gets warmer. And if you pump loads of salt in there, the water gets heavier because now it's got salt in. So these constants are something to do with water. Ocean water. Okay. So we've got the density difference equal 1 over k. And I might try and draw my 2 bucket picture again. For this one having T1 and S1, this one having temperature T2 and S2, with some flow between them. So flow Q, this one's got flow Q going back again. And that flow Q, whichever way it's going, tends to get the tends to mix things up. Okay. Yeah, I suppose that's a baseline. Rho naught is a kind of baseline density, and then alpha and beta represent partial derivatives of the density with respect to temperature and salinity. Yeah, don't ask me to do a Kelly row. The justification behind this is, yeah, sure, density is complicated, but Taylor series, and then this is a Taylor series. It has a value, and then it has some correction terms that are linear in the difference. I guess these TNS are relative to a baseline then. Temperature perturbation from whatever temperature and T0 and S0 has to give me rho 0. Yeah, and then there's like some further corrections, but quadratic corrections. Please look up Hessian if you'd like to learn more, or look at some oceanography textbooks if you'd like to know the values of these things. Okay, not important to me right now. I'm on a mission to try and understand this thing. Yeah, okay, let's try and talk about this then. So maybe T1 and T2 are already relative to some sort of normal temperature for the ocean, but you can do something like, There's one more thing I had a box around. Before I start messing around with the equations, I should write down the equations, right? Alright, this equation that I'm writing down is for t and negative t. Oh, okay, I'm jumping the shark. Let's go. Is t2 going to be the negative one? Yeah, sure. And I kind of there's these porous walls that say, fine, this bit of water is all mixed up and different in some way from its surroundings, which have got particular values, which I'm going to call t hat and s hat, instead of writing any more curly t's or curly s's. And maybe this means relative to a temperature of 10 degrees Celsius or something. This thing is a bit hotter than 10 degrees, this bit colder than 10 degrees. These kind of porous walls that try to keep this bit hot and this bit cold. I guess that's representing all of that lovely sunshine on this side that's just like permanently beaming down and keeping things warm over here. So as the water comes in, it's like, wow, you're surrounded by hot water in this bit of the ocean. Off you go then, carry on your oceanic circle. I'll take some hot water with me in this oceanic circle. Having such a great time. And you get to the cold bit where it's all like cloud cover and polar bears or whatever. And everything's very cold. And you lose some temperature to the surrounding here. And then keep moving on your oceanic circle. And you go around. And it gets all kind of mixed up in each of these regions. I guess it's getting mixed up during the travel as well, but it's kind of travelling as it goes. Anyway, there were some different equations that I was writing down about how this thing changes. C, t hats, take away t, and a term here, minus, and this is important to say. On the one hand, this temperature is getting towards t hat, and this one's going towards negative t hat. But also, the temperature is changing. The temperature is changing because it sees some opposite water being pumped in and it's removing this sort of water. So over here, it's removing water at temperature T and adding in water at temperature negative T. Oh no, disaster. Every second that will replace 2Q amount of water and it will change the temperature then by 2T. No, by T. Multiply this together. Only 1, 2. It's only 2 pipes, not 4 pipes. Right, good. I'm making things worse by talking about them. Let's go. Different rate here for how quickly it takes the salts to get to the salt reservoir saltiness, and also here a rate for how that salt is being moved through the pipes. Okay. And then, so these things are all linked together because T appears in the different equations and also in this Q term here. So why don't I just plug it all back in, right? So this would be 1 over K. The ones would cancel and I'd get a rho naught effect. I'm going to do the difference of these two terms, alpha T plus beta S1, take away the other one, so a factor of 2 for the difference. I think that's true. Doesn't matter too much to me whether there's a factor of 2 there or not, actually. So the sort of density difference is something to do with alpha T and beta S, where that's now the difference. I'm not thinking about the difference between the two. Rho 1 and rho 2, rho 1 on the left, rho 2 on the right. Which way around doesn't seem to matter very much to me because there's this mod Q effect going on. So I kind of want to imagine putting that in here. Yeah, which is in fact the different equations that they talked about, isn't it? To plug that into there. So why do you then look back at flux? Why not just solve it? Why not just solve it and take whatever you get? I guess plugging it in, you've got to actually satisfy the equation as well. You might ask, what's the flow? Because at the moment, I could plug that in for Q and just go and put it in a computer, see what happens. Might just do that. Might just do that. People who've seen the stream before will know that I only speak one programming language, and it's not even a very good one. So we're going to boot up MATLAB and have a go at just dealing with that. See what happens. Ooh. This is just slight. That's a slightly odd thing, isn't it? Hang on. This is slightly tech-wise. There we go. That was annoying me. Okay, let's get rid of that and zoom in here. And well, it could be in this folder, why not? So, what do I need to do? I need to do something like. Now, I haven't bothered to non-dimensionalize, so look how bad this is going to be. This is going to be quite bad because I need a value of C. I need a value of D, which I think we're imagining to be less. D over C is like 1/10, maybe 1/6. I need a value of T hat and a value of S hat. Welcome to the stream. We're using primes now. T prime is going to be 1, S prime can be 1 as well because I don't actually care about the values. And what we're going to do is define some equations. Do I need some values of alpha and beta as well? It's quite tempting to just define like alpha and beta to be, define A and B to be pretty much alpha and pretty much beta. That's almost a non-dimensionalization, but not quite. What we're doing here is quite a lazy non-dimensionalization where I just take loads of things to be the number 1 to see what happens. Okay, so let's throw in some random parameters just to see what we can build. I'm not even going to bother with K. So, what are we doing? We're going to have a vector that's going to keep track of S and T. And we're going to supply a differential equation. The way you do that in MATLAB is something like this, isn't it? So you define a function, which is at any given point you need to explain how the value of the function is changing. So first, my vector is going to be, my vector y is going to store S and T. So in here, I need a term to measure how everything's gone away. I need a term to measure how things are changing with time. I've lost the thing that I was trying to type. There, it's all back again. Okay. Okay, so this needs to be C times, and then it'll be T prime minus T, which is the thing I'm storing in the first component. Am I doing T first? I'll do T first and then S. Minus, this is maybe the worst code I've ever written. 2 times, and then there's a whole load of mess here. Which we'll currently write as Q, times, and that'll be Y1. And then in the other term, we do something very similar with values of S prime. Take away, I'm storing S in the second component of Y. The absolute value of 2 times Q times, in this case, it's S. Okay. Need to replace Q in that with an actual expression because at the moment it doesn't know what Q is. So I need to tell it what Q does. I'm regretting all of the letters and not non-dimensionalizing. I guess I'm proving a point that non-dimensionalization is actually good. Where has this gone? It's gone over there. Okay. So I need to type something about this. So Q is going to be something like, probably do want a parameter in here. Let's just leave it for now. A times T, which is Y1, whoops, plus B times Y2. It's my expression for Q, which I've now realised I want actually inside here. 2 times, and then brackets around all of the Q stuff. If in doubt, put brackets on it. And that'll be all fine, I think. Is that all just all fine? No, it's not happy at all. Why do I do this to myself? Why don't I do live coding? I'm not good at coding. I'm very, very lazy. It's not happy with my Y. Doesn't know about Y. It's not how you specify functions in MATLAB. Is that how you specify functions? Yeah, that's good enough. Okay, good. The reason I like MATLAB is that it has a sort of built-in integrator. I mean, lots of languages do, don't they? But this one definitely does. That lets you just integrate things from like time is 0 to 1. Let's go 0 to 10 just to see what happens. Where you give it starting values. I think I'm going to start with 1 and 2 just to check I can make this run. That should just run. And then what do I want to call this? Like S is, so T is what we were storing in the first component of Y, and S is what we're storing in the second component. That's not too bad. I can just plot T. I can plot temperature over time, not T prime, temperature over time. Dodgy code is maybe the only thing that is a true constant on Chill Maths, to sort of try and make just random pictures of how things might change over time. Okay, so this is showing a picture of how the temperature changed, started at 1, and the temperature decreased because of some flow happening over time, but then eventually ended up getting back towards the number 1 again. I don't know why it's done that, but I'm interested. Was 1 a special number? Yeah, T prime and S prime are both 1. Okay, maybe I'll start it off more temperature, more salt. So now it's started at number 2 and it's ended up at the number 1 again, which makes me think I've done something wrong. Oh, I suppose ending up at a kind of consistent point is a symptom of having a steady state. So if I really think about it, I could change these starting values and maybe it won't matter how out of balance I start, I end up at a kind of stable point, which seems to correspond to about 1 on the temperature scale. Let's have a look at what salinity is doing at the same time. Oops. Oh, that's how you do that. Salinity is coming down and then settling out at something like this. Okay. Also looks like the number 1, which makes me suspicious. So if these things are both 1, then that'll be 0, and the flux will be, oh my goodness, I set A and B to both be the number 1, so the density difference isn't really doing very much there. Let's say that B is 0.5 or something more interesting. Okay, behind the scenes, different picture of what's happening. It's now settling off to some interesting value of the salinity. Okay. Something weird going on there as well. And we can do a version of that plot that we saw, right? To show what's happening to S and T, and that's a terrible picture. There was a salinity temperature picture going on somewhere. Let's try and recreate that. Oh no, we really can't because of all the terrible differences in constants that we've used. Instead, let's have a look at lots of different starting points. So let's do something like that to make it a little bit more classy. And I could do something like for I is 1 to 10. I want you to run this. Hold on is MATLAB code for please show me this lots of times. can change that number to look at what happens if you start at different points from 1 to 10, and how it doesn't seem to matter where you change that, you always seem to be ending up down at the fixed point over here. Whee, going in there. Oh, sometimes going round. This looks like one of those stable nodes they were talking about in the paper. The things are collapsing in towards this stable point. 0.8 salinity, 0.7 temperature. So a little bit out of balance. S prime and T prime are both the number 1, I think. Yeah. So a little bit out of balance as a result of the density differences driving a flow and sustaining that flow. Okay, so the calculation for looking for steady points is complicated and involves that weird hat-shaped graph. But we could keep doing things like this. So I could change how much flow you get. How much oceanic flow do you get as a result of, oh dear. How much oceanic flow do you get as a result of the temperature and salinity changes? For me, that's the numbers A and B, where I could say, maybe you don't get very much flow. Maybe I'll divide these both by 10 and see how that changes things. So that didn't seem to change things very much at all. Yeah, maybe really not very much flow. And then this is just coming towards number 1. So okay, so that's not very exciting. Maybe if I change the, if I change these to be large, we get some interesting pictures like this, where things come right down. Okay, and then the paper talks about there sometimes being different fixed points. I'm going to try and find that region just by trial and error a little bit. I think I want to try larger numbers just to see what happens. Let's see if I can break it. I don't think I'm breaking it yet. And there's a possibility that it's only the ratio of these numbers that matters. Let's just quickly check that. That didn't change very much, did it? Change the ratio of those numbers. All sorts of fun that you can have messing around with absolutely terrible code. Okay, so I'm glad I got the different equations to actually work. I'm not certain I've done it correctly, so I'm going to have a quick look at that. If you're playing along at home, you might like to think about whether that should be the number D, which doesn't seem to be in my code at all at the moment. I swear that changed one line and nothing else. Yeah. Top tier. Ooh, no, it has changed things. It's changed things over here. There's some interesting behaviour going on. So get as close to that fixed point in there. Ah, right, okay, let's make these numbers not huge. Okay, maybe we're playing now. Yeah, now we're playing games. Now we're playing games. Okay. So if you make the relaxation rates actually different, I have the number C in both of these different equations, which I don't think was correct. Oh, there, yeah, I've missed that this was the letter D. Then you start to get interesting behaviour, and this is one of those spirals. Starting at different temperatures, salinities. We've got this thing collapsing towards a stable point, but in a slightly different way. Okay, so that's reminded me that C and D being different seems important. I do want to see if I can change starting points. It looks like there's something going on here, right? There's something going on here. I maybe don't want to start so far over there. That seems to be all bunching up. So maybe I'll start. I'll take away my maths license. Well, I don't know what's going on there. It's all gone up there. Can I change that to 3? That's the weirdest way to do a parametric sweep ever. The temptation to make this code slightly better. I think we did the first pass on the code in like 3 minutes. The temptation to go back and just do it properly is very strong. What were all these? What was all this about? Yeah, it kind of looks like it's avoiding something. Let's go for more of a parametric sweep like this. So this is going to be T-vals, it's sort of a linspace thing between 0 and 5 with, I don't know, 11 of them, and something similar for salinity values. And then start for I in the T vowels, for J in the S vowels. I've already forgotten which way around these are. T is the first one. Can I do that? I think I can do that. Indent properly. Don't need the semicolons, always forget that. Does that work? Yeah, that sort of works. If by sort of works you mean horrendous picture. Really nasty. Look at this dynamics. Look how it's collapsing down. Oh, okay, great. Don't know if this has told me anything about the ocean yet. I suppose it would be nice to know what the flux is at different times. So this chart, I've had enough of it, I think. Not sure it's showing me something super exciting. So instead I'm going to go back to plotting temperature and salinity, which is not hard. I have time and I have temperature. Let's go for temperature first. That way that temperature was changing in a weird and bouncing up and down way. Or we could look at salinity, or we could look at the flux in the pipe, right? That would be good. So that's minus AT plus B times S. Yeah, positive then negative. If I deleted the bit that solves the ODE, I think I have. Don't mind me, just redoing something I just did. There we go, T minus A times T plus B times S. Good, there we go. This is pretty bad. Okay, getting there, I think. So you can have this setup where the flow in the pipe is going in one direction and then after a while going in the other direction, so kind of reversal. So it ends up at this point with negative numbers for the flow. Right, so we're in a case where there is a stable point. It looks like there is a stable solution down here somewhere with reverse flow, which I think means there's another one with positive flow. I kind of want to try and find now. That's something to do with my starting values? Possibly? Let's give that a go. Let's try random stuff. Yeah, not that. That's gone to the negative solution again. Not that. That's gone to the negative solution. I don't know what I'm doing. Is it true that if you get a negative solution in that world that they showed me with the stable solution graph, if you have a negative solution, do you always have a positive solution as well? Okay, other questions are available. I think maybe refusing to non-dimensionalize for the code was a really bad idea that now means I can't compare with the paper. Back to the paper. Can I go back to the paper? Yes, we can. Ah, okay. So I managed to find this parameter range where in their coordinates but not mine, R, which is maybe the ratio of B and A, is 2, delta is 1/6 and lambda is 1/5. And I can't immediately copy those numbers through, can I? Okay. So as this crosses the density 0 line, this will change, or F0. Oh, maybe it wasn't density, it was F all along. Sort of related concept. As this crosses the F=0 line, this will reverse the direction of the flow. So you end up with this solution on the right with a positive flow and that solution on the left with a negative flow. And I think I've only seen this one so far. Be nice to find some numbers that do that, including the spirally behaviour. We briefly saw that, didn't we? We saw something like that anyway. Sort of spiral going on. Two negative solutions and the positive solutions. Let's try and wrap it up. We got 5 minutes on the clock. So this paper's been trying to tell us about density-driven ocean circulation, where density is something to do with temperature and salinity, and the flow that you get as a result. And it's surprisingly complicated, I think. If you have a situation where your water held at distance from each other is being water at a distance from more water, let's try and be eloquent. If you have two reservoirs of water pulled in different directions but connected by some flow, that flow can try and counteract some of the tension between the two reservoirs being pulled in different directions. And there's some stable solutions. Sometimes it's the case that the water that's hotter ends up more dense, and thus the deep oceanic flow will go away from that region. And sometimes the hot water ends up being less dense. It's to do with weather. Yeah, it's to do with a complicated, not obvious way that salinity and temperature can move between the two regions, and when they get there, affect density in different directions with different parameters, which could have either effect. Maybe salinity is what determines the direction of flow. If lots of salt ends up in one place, then the water there is very dense, and that might be more important than whatever the temperature is doing. Or maybe the temperature is the important thing. And I think I've heard people say temperature-driven flow and salinity-driven flow and not really understood what they meant. But those things work against each other, and if you see some flow that corresponds to one of them, then maybe that's like whether alpha delta T is bigger than or smaller than beta delta S. Those things are opposite directions. Okay. So before I looked at this 2 hours ago, I didn't really understand why there were any mod signs, or why, although you have mod signs, the solutions don't end up symmetric. Let's see if I can piece that together now. You know, like these 3 numbers for F, some of them are negative, some of them are positive, they're not equal and opposite. So you might have a solution where the flow is in one direction but not the other. Oh, I need to use this one for this one. You might have a situation where, because of the fluid parameters, you get flow in a steady state like this, and not the other way around. And it's the size of the flow that appears in the differential equations. Mod Q is the thing that appears in the differential equations. But then actually what Q is depends on the density difference. So there's always going to be some flow from the left box to the right box. But whether it's density driven and deep down is different from whether the density difference might be the other way around, and then the flow from the left box to the right box might be up on the surface to balance out the volumes. And I'm not certain it's healthy for me to think about it as density driving one of them and the other one being a consequence by conservation of mass, because it's all one system. So kind of having a 2-step description feels a little bit off. I think I'll stick there for now. Current understanding. Okay, let's look back at the title. Oh, that's over here. Look back at the title and think about what we've learned. was a chill math stream. We thought about the effects of maths on the ocean, and the effect of chilling on the ocean. We've seen a kind of model about connected reservoirs of water, how flow might go between them to balance them out, despite them being pulled in different directions by being at the equator and the North Pole. And the steady states of that are pretty complicated. So when people try to tell me about this paper, or tell me about work following on from this paper, I now realise that some of the stuff people have told me about this isn't in this paper. There's this lovely graph and a quadratic thing with all sorts going on to explain where those stationary points are. Such as a quadratic. Might just be a quadratic. Yeah. All sorts going on. And only some of it's in the paper. Yeah, and the real ocean's much worse. Way more than 2, and all sorts going on. I'm surprised there's no evaporation. I've underlined it over here. Oh gosh, I don't know what to point anymore. I've underlined evaporation over here, and often when people tell me about this topic, there's some evaporation going on. They include it. I put E's on this picture, and then there's none in the paper. So I guess that's somebody else's paper, and further research, further reading needed. Embrace the confusion. Yeah, this is a bit of a different thing. I like to mix it up. Sometimes we do step questions. Sometimes we do learning number theory. Sometimes we do just what I would otherwise be doing on a Sunday afternoon, perhaps, which might be trying to understand a paper I've never understood. Right, thanks, chat. Thanks for coming along the journey with me. Don't worry, next week, not this. So I think I'm back next week for Chill Maths. What's my opinion on giant tube worms? Oh, like in the movie. Before we leave the ocean. Wait, no, what's the ocean link here, Herb? Go on. Before we move on from the ocean. Like in real life. I thought this was going to be a gene thing, but no. Okay, I'm Googling it now. I don't think I have an opinion on these. What? It's a giant tube worm. It's a thing. They live near hydrothermal vents. That sounds cool. They can be 3 meters long. Terrifying. Week 3 of recommending murderous maths. Where do I write that? So I actually remember to go and look at murderous maths. We looked at the website very briefly last week, didn't we? And then I forgot about it for an entire week until you said this again. But I don't think I've formed an opinion yet on giant tube worms. If you'd like to influence my opinion, you can have a go at that. Otherwise, I think I'm going to wrap up. It's your first time seeing the stream. Don't worry, it's not always like this. Well, always a bit like this, isn't it? It's not like it's normally less weird. Very good worms. Okay, that's an opinion that I can start. And there's a starting point for me. Okay, thanks for hanging around. I will see some of you on Thursday, and see you next week. Just punched my desk. Right, before I hurt myself, let's go.